Good morning, students. In the previous class, that is class 4 for the chapter Chemical Kinetics, I already covered, that is the important long question, the second long question, that is kinetics of first order. Next, its characteristics, half-life period, and some usual relation relating to some problems. Then today in class 5, that is last class of the chapter Chemical Kinetics, I will try to cover rest part, that is what is collision theory of a reaction rate, activation energy, threshold energy, little bit idea about activated complex, and the last one is Arrhenius equation. So before starting the class, let us solve one or two problems relating to the previous class. That means we cover, that is the first order kinetics, and some relations are there. I repeat, 2 to 3 relations are there. Mark that. That is T 75% is equal to 2T half. T 99.9% is equal to 10T half. T 99.9% is equal to 5T 75. T 99.9% is equal to 3T 90, and T 99% is equal to 2T 90. These are some relations are there, as well as one problem carrying 2 mark. In the previous, I covered, that is this one, first one, that is T 75 is equal to T half, or prove that the time required for the completion of 75% for a first order reaction is equivalent to nearly 2 times that of the half-life period. Today I solve the second one, that is prove that T 99.9% is equal to 10 T half, or the time required for the completion of 99.9% for a first order reaction is nearly equal to the 10 times that of the half-life period. Mark that. First is T 99.9%. By definition, that is 2.303 by K log base 10. Initial is 100. 100 minus 99.9 is equivalent to 2.303. We put this value of K, that is 2.303 into 0.3010 by T half, or into T half, into log base 10. It is 100 minus 99.9, that is 0.1. 0.1 means 1 by 10. 1 by 10, 10 moves to here, that is 1000. 1000 means 10 to the power 3. Remember that? It is cancel out. That is 10 to the power 3. 3 log 10. 3 into T half divided by 0.3010. We know that log 10 is equal to 1. So mark that 3 by 0.3, it is nearly equal to 10 T half. Proved. That is T 99.9% nearly equal to 10 T half. Similarly, we prove the another formula is there. Next, switch over to another one or two type of problem. Next question is question number 2. Half-life of a first order reaction is 60 days. Half-life of a first order reaction is 60 days. Calculate the fraction or calculate the amount left after 240 days. Mark the question. What are the data given? Data is half life given and total lifetime is given. Answer. Mark that. How we solve it? Given that T half is equal to 60 days and total time, that is capital T, is equal to 240 days. We know a formula, that is N means number of half-life. How we calculate a number of half-life? Number of half-life is equal to total lifetime by T half. That is 240 by 60 is equal to 4. It is one formula already covered. Simultaneously another one formula is there. The fraction of substance left. How we calculate? That is N. That is, what is N? The fraction of substance left after N half-life is equal to initial amount into 1 by 2 to the power N. By putting this value, it is given, let it is taken as N naught into 1 by 2 to the power 4. That means initial amount by 16. Initial amount by 16% is like, if we calculate the percentage value, then 6.25% of its initial value. It is one type of problem relating to fast order kinetics carrying 2 marks. Then switch over to another type of problem. Mark that. What is the question? Question number 3. Mark that. Rate constant for a fast order reaction. Rate constant for a fast order reaction is 23.06 second inverse. 23.03 second inverse. Then calculate the time required. Then calculate the time required during which the concentration or the fraction of substance is reduced to 1 by 4th of its initial value. Mark the question. Answer. Mark the question. What are the data given? Data given, rate constant, that is a K given. Mark that. Given K is equal to 23.03 second inverse. K is given. Then question is calculated time T. T is a question mark. As a result of which the concentration is reduced to 1 by 4 of its initial. Suppose or let initial concentration is equal to A moles per liter. Then final concentration is equal to A by 4 moles per liter. Then applying the formula for fast order kinetics, we know that is T is equal to 2.303 by K log base 10 initial by final concentration. We know it is according to the fast order kinetics. So if we apply this data to this expression, what we observe? Equal to 2.303 by 23.03 log base 10. Initial is A, final is A by 4. Mark that. What happened? This is equivalent to 2303 by 000 into 00 by 2303 into log base 10. It is A by 4 means 4 by A. A cancel, 4 means to the power 4. This one cancel, this one cancel. That is 1 by 10 into 2 log 2, 2 into log 2. That is 0.3010. We know value of log 2 is equal to 0.3010. So mark that this is equal to 0.6020 by 10, that is 0.6 second. Mark that the question is calculate the time required to reduce the concentration to 1 by 4th of its initial. The answer is 0.6 second. After 0.6 second, the final initial concentration is reduced to 1 by 4th of its initial value. That is, final concentration is 1 by 4th of its initial value. This is the little idea about some problem relating to the first order kinetics. Next, switch over to the second one. Today class, that is known as collision theory of reaction rate. Next is collision theory of reaction rate. 4 to 5 point is there in this postulate of the collision theory of reaction rate. 4 to 5 point are there. We discuss one by one. Point 1 is every reactants are made up of molecules. Mark that. What is the point 1? Every reactants are made up of molecules. Every reactants are made up of molecules. Point 2. What is the point 2? The molecules are always in a state of rapid random motion and hence collide among themselves. Second point is molecules are always in a state of rapid random motion and hence collide with each other. What is the point 3? A chemical reaction takes place only due to the collision among themselves. Third point is a chemical reaction takes place only by the intermolecular collision between the reactant molecules, between the reactants molecules. Next point is all the collisions are not effective one. During the intermolecular collision, these are not able to bring about the product. All intermolecular collision are not able to bring about the product. Mark that. All intermolecular collision are not able to bring about the products. Next is only effective collisions able to bring about the product. Next point, mark that. Next point is only effective collision are able to bring about the product. Next point, what do you mean by effective collision? Effective collision is one in which reactant molecule possess a minimum certain value of energy, that is known as threshold energy. I repeat again. All collisions are not effective one. All collisions are not able to bring about the product. Only effective collisions able to bring about the product. What is effective collision? That collision is known as effective collision in which a reactant molecule possesses a minimum certain value of energy, that is known as threshold energy, and are properly oriented. Next point is a collision is said to be effective if the reactant possess a certain minimum value of energy known as threshold energy and are properly oriented. Mark that, the last point again. Molecules are always in a rapid random zigzag ceaseless motion to bring about the collision. A chemical reaction is possible due to the collision, effective collision. All collisions are not effective. Then the collision said to be effective. That collision is a effective collision if in that case the reactant molecule possesses some value of energy, certain minimum value of energy known as the threshold energy, and the orientation must be properly one. Then we discuss about what is threshold energy. It is a 2-mark question for this chapter, chemical kinetics. 2 terms are there, very very important under 2 mark. One is threshold energy, one is activation energy. We discuss one by one. First is threshold energy. First one is threshold energy. Symbol is ETH. What do you mean by threshold energy? It is defined as the amount of energy possessed by the reactant. It is the minimum amount of energy possessed by the reactant, as a result of which the reactant jump over the energy barrier to bring about the product. I repeat again. It is the minimum amount of energy possessed by the reactant, as a result of which they are able to jump over the barrier, energy barrier, and to bring about the product. Mark that. It is defined as the minimum energy possessed by the reactants as a result of which bring the effective collision, bring about the effective collision and jump over the energy barrier to bring about the product, It is the minimum amount of energy possessed by the reactant as a result of which they are able to bring about an effective collision, as a result of which jump the energy barrier to bring about the product. Mathematically, it is represented as what is the mathematical expression? Mathematically, it is expressed as ETH activation, that is threshold energy, is equal to EA plus EK. This is known as threshold energy. EA is known as activation energy. EK is known as kinetic energy possessed by the reactants. So marking one important thing is that in many of the chemical reaction, reactant do not have possess that minimum amount of energy known as threshold energy. However, from outside, if energy is supplied to the reactant in the form of heat, light, then reactant molecules able to possess that fraction of energy and jump over the energy barrier to bring about the product. Next to discuss another new term is there. What is activation energy? It is also important to mark for council point of view. Next to discuss what is activation energy. Next is activation energy, symbol EA. Activation energy is defined as the minimum extra energy required to the reactant molecules, the minimum extra energy possessed by the reactant molecule, as a result of which they are able to possess the desired threshold energy, bring about effective collision, as a result of which bring about the product. I repeat again. The extra minimum amount of energy required by the reactants, as a result of which they are able to possess, they are able to have the desired threshold energy, as a result of which jump over the energy barrier to bring about the product. I repeat again. It is defined as the extra minimum amount of energy, required by the reactants for which they acquire the desired threshold energy and jump over the energy barrier and hence bring about the product. It is defined as the extra minimum amount of energy required by the reactants for which they are able to possess the desired threshold energy and jump over the energy barrier and hence bring about the product. That is known as activation energy. Mathematically, it is represented as EA is equal to ETH minus EK, where EA is known as activation energy, ETH is known as threshold energy, and EK is known as cardiac energy possessed by the reactant. So from this mathematical expression, activation energy may also be defined as the difference between the threshold energy and energy possessed by the reactant is also known as activation energy. I repeat again. From this mathematical expression, activation energy may be defined as the difference in energy possessed by the threshold energy and energy of the reactant is known as activation energy. So from this data, it is clear that higher is the extra minimum energy required, means higher is the activation energy, then slower is the rate of reaction. Lower is the activation energy, higher is the rate of reaction. Mark that. The important point is there. It is to be noted that, note, point 1, if EA is low, if activation energy is minimum, then faster is the rate of reaction. Point 2, if activation energy is high, then slower is the rate of reaction. So next, in order to understand the energy barrier, activation energy and threshold energy, it is necessary to draw a graphical representation. How energy is required, what is threshold energy, what is activation energy, what is the energy barrier, how it is necessary the reactant to how it is jump over the energy barrier to bring about the product. Most important thing is that during this one new term is there, that is activated complex. So we will now discuss little idea about activated complex. Next we discuss about activated complex. Little idea about activated complex. That means, in other words, it is also otherwise known as a transition state. Transition state. That means, when the reactant react among themselves, chemical reaction nothing but the intermolecular collision, then what happens? All the intermolecular collision are not effective. All the reactants are not able to possess maximum amount of energy. So what happens? From any other source, if energy supplied to the reactant, then they jump over the barrier. After getting required desired amount of energy, they jump over the barrier and possess a maximum energy content and form a complex that is known as activated complex. As it is the highest energy state, in class 11 chemical bonding already covered, that is energy and stability are inversely proportional. Higher the energy, lower the stability. So at that state, form a complex known as activated complex. At that time, two cases arises. If the reaction move forward, then jump over the energy barrier to bring about the product. Unless chances is that they decompose back to form again the initial reactant. So in order to understand this one, I draw a graph, mark that, by taking potential energy versus reaction coordinate. Mark that. A graph is there. This one is known as a reactant. That is energy possessed by reactant is known as ER. It is known as a product. The energy product possessed by the product is known as EP. This difference between the energy, that is del H. Mark that. This is the barrier one. This is the barrier one, is known as EA, means activation energy. Mark that. This state is known as transition state. It is known as transition state. Having maximum energy, it is known as ETH. ETH means threshold energy. So mark that. What happened? Reactant, here is the reactant possess energy ER. By gaining from any other source, by gaining energy, reactant jump over the energy barrier. This point is there. That is maximum energy possessed content at this state. That is known as a transition state. As possess maximum energy being unstable, chances is there to think. If you move forward, then bring about the product. It is the enthalpy, it is heat evolved. This is the graph for reaction profile, the progress profile for exothermic reaction. Come to the point. Important thing, that 2 point is that if this activated complex move forward, if the reaction move forward, then bring about the product. Unless chances is that this one decomposed to bring about the initial reactant. So in order to understand this one, I go through to describe one equation, that is combination of hydrogen and iodine to form hydrogen iodide. Mark that. H2 plus, we know H2 plus I2 give rise to 2HI. Mark that. When hydrogen combines with iodine, one transition state is there, that is HI. Mark that. It is the reactant. It is the product. It is the transition state. Unstable state. It is unstable state. Mark that. When hydrogen combines with iodine, by gaining a desired energy from the other source, move to the jump over the energy barrier, possess maximum energy content, form a transition state. In this transition state, bond breaking, old bonds are broken down while new bonds are formed. So chances is that this old bond between H and I break down, new bond between HI and HI form. If then jump over the energy barrier to bring about the product, unless they also decompose back to form the reactant. This is a little idea about activated complex or transition state. Next we discuss about how temperature depends upon the rate of reaction or rate constant. Dependence of temperature on rate constant, within bracket, that is Arrhenius equation. We know that temperature plays a significant role while deciding the rate of reaction. Already over. That is in class 1, the factors affecting rate of reaction, 1 point is there. That is, on increasing temperature, For every 10 degree centigrade rise in temperature, rate of reaction nearly double or triple. One term is there that is known as temperature coefficient. So it is clear that temperature increases the rate of reaction. Means while increasing temperature, number of collision increases. Number of collision increases means number of effective collision increases. So from this it is clear that temperature play an important role for the rate of reaction and also rate constant. So how temperature depends upon rate of reaction as well as rate constant, that is given by Arrhenius in the form of one equation that is known as Arrhenius equation, which is represented as K is equal to A e to the power minus EA by RT. This equation is known as Arrhenius equation, where K is known as rate constant or velocity constant or specific reaction rate. Next, A is known as a constant, it is a constant known as a frequency factor. Next, E is known as exponential term. Next, EA is known as activation energy. R is known as universal gas constant. T is known as absolute temperature. This equation is known as Arrhenius equation. So taking logarithm on both sides of the above equation, we have taking logarithm on both sides of the above equation, we have ln k is equal to, it is one term, log a into b is equal to log a plus log b, that is ln a. As exponential term is there, cancel out EA by RT. Ln means logarithm base e. We have to transfer logarithm base 10, then we have to multiply 2.303. That is on 2.303 log base 10 k is equal to 2.303 log base 10 a minus EA by RT. Next, dividing 2.303 to each term. Dividing 2.303 to each term, we have, or this one, log k is equal to log a minus EA by 2.303 R into 1 by T. Mark that. It is an equation of a straight line. It is an equation of a straight line in the form of y is equal to mx plus c. That is slope intercept form. Mark that. It is also required expression for Arrhenius equation in logarithm form. That is equation 1, it is equation 2 in logarithm form. And also it is y, it is c, it is m, it is x. Y is equal to mx plus c. Equation of a straight line in the slope intercept form. So if we plot a graph by taking y versus x, y means log k versus x means 1 by t, then we have a graph like this. This is known as y-intercept, that is log a, while slope m is equal to minus EA by 2.303 R. where R is known as universal gas constant. Its value is 8.314 joule per Kelvin per second. So if this value is given, then slope is given, we calculate the activation energy. Or if activation energy is given, then we can calculate the slope. Next, this Arrhenius equation also represented in logarithm form at two different temperatures. Mark that. Suppose when the temperature is T1, let the rate constant is K1. When the temperature is T2, let the rate constant is K2. Then one is able to represent the Arrhenius equation at two different temperatures. How it is? Mark that. Let the rate constant are K1 and K2 at temperature T1 and T2. So if temperature T1, for temperature T1, mark the equation, that is log K1 is equal to log A minus EA by 2.303 RT1, equation 1. And for temperature T2, the equation becomes, that is log 10 K2 is equal to log 10 A minus EA by 2.303 RT2. If we subtract equation 1 from equation 2, that is subtracting equation, that is equation 2 minus equation 1, we have, that is left minus left is equal to right minus right. Log A minus log B is equal to log A by B. That is log K2 by K1 is equal to this term minus this term cancel out. This term minus this one, minus and plus, that is taking a common EA by 2.303 R by taking a common 1 by T1 minus 1 by T2. I repeat again, this one minus this one, log A minus log B is equal to log A by B. This one cancel out. So this value minus this value minus and plus. So EA by 2.303 RT1 minus EA by 2.303 RT2. Taking a common EA by 2.303 R, 1 by T1 minus 1 by T2. Or that is log base 10 K2 by K1 is equal to EA by 2.303 R T2 minus T1 by T1 into T2. Mark that. It is the desired equation, it is the required equation of Arrhenius equation in logarithm form at two different temperatures. So Arrhenius equation represents three forms. One is K, first one without logarithm form. Second one is a logarithm form at particular temperature. Third one is a logarithm form at two different temperatures. Now solve one or two problem by taking this formula. Question. The rate constant is 1.2 into 10 to the power minus 3 second inverse at temperature 27 degrees centigrade and 2.4 into 10 to the power minus 3 second inverse at 37 degrees centigrade. Calculate the energy of activation. activation. Mark the answer. What is the data given? K1 given, K2 given, T1 given, T2 given. Answer. Given that K1 is equal to 1.2 into 10 to the power minus 3. K2 is equal to 2.4 into 10 to the power minus 3. T1 is equal to 27 plus 273, that is 300 Kelvin. T2 is equal to 37 plus 273, that is 310 Kelvin. So putting this data in the equation, putting the value of K1, K2, T1, T2 in this equation, we have, mark that, log base 10, 2.4 into 10 to the power minus 3 by 1.2 into 10 to the power minus 3 is equal to EA, we have to calculate EA by 2.303 into R 8.314. It is 310 minus 300 by 300 into 310. This cancel out, that is log 2. Log 2, then we calculate EA, R is equal to log 2 value is 0.3010 is equal to EA by 2.303 into 8.314 into 10 into 300 into 310. Our aim is to calculate EA. That is EA is equal to 2.303 into 8.314, 0.3010 into 300 into 310 divided by 10. This value is nearly equal to 53.6 kilojoule. It is a 2-mark question relating to the Arrhenius equation logarithm. Switch over to another one question. What is that question? Mark that. Question number 2. The rate of a reaction becomes a double. Rate of a reaction becomes a double when temperature increases from 27 degrees Celsius to 37 degrees Celsius. Calculate the activation energy. Mark that. The rate of a reaction becomes a double when temperature increases from 27 to 37 degrees. So we apply the data for the formula, that is answer. Log base 10 K2 by K1. Suppose K1, that is K2 is double that of, that is 2 K1. In place of K2 we write as it is double, we write it this much. So log K2 by K1 is equal to 2.30 EA by 2.303, then R 8.314 into T2 by T1. T2 is equal to 310 Kelvin minus 300 Kelvin divided by 300 into 310. Mark that. Our aim is to calculate this one. So E1 is equal to, it is at log 2, that is 0.3010, 2.303, 8.314 into 300 into 310 by 10. This value also nearly equal to 53.6 kilojoule per mole. These are some numerical relating to the Arrhenius equation. Last, another one problem is there. Let us discuss that one. Third one. Activation energy, that is EA, is 0 Then calculate the rate constant at 30 degrees Celsius if the value of rate constant at 40 degrees Celsius is 2.3 into 10 to the power minus 2 second inverse. Mark that. What is the question? Question given that activation energy is 0. That means we know the formula. Log 10 K2 by K1 is equal to EA by 2.303 R T2 minus T1 by T1 into T2. So from this relation, given that this one is 0, that means the total term is 0, or log 10 K2 by K1 is equal to 0, that is log 1, log 1 is 0. So from this expression it is clear that K1 is equal to K2. That means here temperature has no role. What are the value? At 40 degrees centigrade, this is the rate constant value. So similarly, at 30 degrees centigrade, the rate constant also similar because K1 is equal to K2.